Good morning. Today we are going to discussing about logic gates. So this is the very last topic of this module. So we have discussed all the other topics. So a digital circuit with one or more input signals but only one output signal is called a logic gate. Usually a logic gate will have one or two inputs or more than two input signal but only one output. Such devices are called, or the digital circuits are called logic gates. Since a logic gate is a switching circuit, that is digital circuit, its output can have only one of the two possible states, either a high voltage which can be represented by 1 or a low voltage which is 0. It is either on or off. Whether the output voltage of logic gate is high or low will depend upon the conditions at its input. That is, the logic circuit is a switching device, so it will have only two states, on state or off state, or a high state or low states. High state is represented by high voltage 1 and low state by 0. Okay, and its output is dependent upon the value of the inputs. Okay, the figure shows the this table. In this table and this figure gives you a logic gate. So here is the voltage, DC voltage. Here two switches are given and this is bulb. So we can see this is switch 1 and this is switch 2, and here it is the bulb. When the switch S1 is open, when both the switches are open, S1 and S2 are open, bulb is off. That is, no current will flow through the circuit when these two switches are open. When switch S1 is open and S2 is closed, then the current will flow through this circuit. Will not flow through this switch, but there is a possibility of flowing current through this circuit, but since no current flowing through this, no current will flow through the circuit, so the bulb will be off. And again, if it is this S1 is closed and S2 is open, again no current will flow to the bulb, then it is off. If both the switches are closed, then the bulb will switch on. Okay, so this circuit is acting like a switch. So this can be represented by a truth table. This open state as 0 0 and the output is 0 0 1 0, and closed state 1. Closed means the circuit is conducting, and 0 open for open state and the output is 0. When it is both the switches are closed, the inputs are 1 and 1 and the output is 1. Okay, so this is a symbol representation of a logic gates. In itself, the circuit is not actually a logic gate, but the logic is similar. The actual gate circuit are made with diodes and transistors. In other words, switches S1 and S2 are replaced by diodes or transistors. So a digital circuit or a logic circuit is constructed by using transistors and diodes. Okay, when S1 and S2 are so this is the explanation of that table. We have already explained that table. The four possible combination of switches S1 and S2 are shown in the table on the previous page. It is clear that when either of the switches or both are open, the bulb is off. In binary language, when either of the inputs or both the inputs are low, the output is low. When both the switches are closed, the bulb is on. Okay. So it is usual to practice to show the conditions of at the input and output of the logic gate in a binary form, as in the form of table, and such table is known as truth table. This is shown in this figure. So this is the truth table for this circuit. That is, The input-output states are represented by binary numbers. So this is the truth table representing this circuit. Okay. So there are three basic logic gates. They are OR gate, AND gate, and NOT gate. Okay, these are the three logic gates which will have one or more input signals but only one output signal. So all these gates can be analyzed by constructing the truth table. Okay. So we shall first discuss these three basic logic gates and then the combination of these two. The following points may be noted about logic gates. A binary 0 represents 0 voltage and binary 1 represents plus 5 volt. It is common to refer to binary 0 as low input or output and binary 1 as high input or output. Okay, so 0 state means 0 voltage and binary 1 means plus 5 volt. So this is a usual convention we are using in logic gates. A logic gate has only one output signal. The output will depend upon the input signal or signals and the type of gate. Okay, the operation of logic gate may be described either by truth table or Boolean algebra. So let's check how the logic gates are described using truth table or Boolean algebra. So first we will discuss about OR gate. An OR gate is a logic gate that has two or more inputs but only one output. However, the output Y of an OR gate is low when all inputs are low. The output Y of an OR gate is high if any or all of the inputs are high. It is called OR gate because the output is high if any or all the inputs are high. For the same reason, an OR gate is sometimes called any or all gate. For example, consider a 2-input OR gate. The output Y will be high if either or both inputs are high. So we are discussing about OR gate. It is a 2-input signal and have only one output. Its output will be high if any of the inputs is high or both the inputs are high. So that's why it is known as any or all gate. Okay, and its operation figure, where is the figure 26.1? Yeah, this is the figure. Here we have shown the figure. Here there are two diodes D1 and D2 and this is the load resistance RL. Okay, and this is plus 5 volt DC supply. And what's happening here? So the figure shows one way to build a 2-input OR gate, while the second figure shows simplified schematic diagram. So I can show you this. So yeah, this is the schematic diagram and this is the circuit. Okay, so this is symbolized as a switch A and this as B, switch B. So what happens here? The input voltages are labeled as A and B while the output voltage is Y. Note that negative terminal of the battery is grounded and corresponds to 0 state or lower level. The positive terminal of the battery plus Y corresponds to 1 state. There are only 4 input-output possibilities. Since this is a 2-input system, there are only 4 possibilities of inputs combination, input-output combination. Okay, so we have shown here the truth table. When both A and B are connected to ground, both diodes are non-conducting. Means when both A and B connected to ground means no signal at the input. So A is equal to 0 and B is equal to 0. Then the output is 0. That is no current is flowing through the circuit. So no voltage drop across R. Okay. When A is connected to ground and B connected to the positive terminal of the battery, diode D2 is forward biased and D1 is non-conducted. Therefore, diode D2 conducts and the output voltage is ideally plus 5 volt. In terms of binary, when A is equal to 0, B equal to 1, Y is equal to 1. That means A connected to ground and B connected to the positive terminal of the factory. That means this is not conducting but this is conducting. That means current we get an output at the load resistance. So in the binary form, this can be represented as 0 input at A and one output at B. The output is 1. Similarly, if A is connected to the positive terminal and B is connected to ground, the truth table is like this: 1 and 0, 1 at A and 0 at B, then the output will be 1. That is, one diode will be conducting, though the other is not conducting. And when both the terminals are connected to the positive terminal, both are conducting, again the voltage will be 1, okay, or plus 5 volts. So this is the working of this OR gate. It is clear from the truth table that for OR gate, the output is high if any or all of the inputs are high. The only way to get a low output is by having all inputs low. So this is the symbol of OR gate. This is a symbol of OR gate. So the Boolean expression for this OR gate can be represented by A plus B is equal to Y, but this is not plus. We call it as the operation OR. So we are reading it as A or B equal to Y. Since it is an OR gate, we call this operation as OR operation. So A or B is equal to Y is the Boolean expression, and this operation is like this: 0 or 0 gives 0, 0 or 1 gives 1, 1 or 0 gives 1, 1 or 1 gives 1. Okay, so this is the Boolean expression work, and according to this, the truth table, this gate is working. Okay. And next gate is AND gate. AND gate is a logic gate that has 2 or more inputs but only one output, the similar. And the output Y of AND gate is high when all the inputs are high. However, the output Y of AND gate is low if any or all inputs are low. So, compared to OR gate, the AND gate have high output only if all the inputs are high, and output is low if any of the inputs or all the inputs are low. That is the particularity of AND gate compared to OR gate. So we can represent an AND gate circuit like this. So here both the diodes are connected in a reverse manner. Okay, and this is the load resistance, and this is the schematic representation of this diagram. So when both A and B are connected to the ground, both the diodes are forward biased because this is the negative terminal. So when both these are connected to 0 or ground, this will be forward biased, hence they conduct current. Consequently, the two diodes are grounded and output voltage is 0. In terms of binary, when A is equal to 0, B is equal to 0, then B is equal to 0. When A is connected to the ground and B connected to the positive terminal of the battery, diode D1 is forward biased while D2 will not conduct. Therefore, diode D1 conducts and is grounded. Again, output voltage will be 0. In the binary form, we can represent it as A is equal to 0 is equal to B equal to 1, then Y is equal to 0. Okay, similarly, when the third case is when B connected to the ground and A to the positive terminal of the battery, the role of diodes are interchanged as from the previous case. Then now the diode D2 will conduct while D1 does not conduct. As a result, Diode D2 is grounded and again the output voltage is 0. In binary terms we can represent it as 1 0 is equal to 0. When both the terminals A and B are connected to the positive terminal of the battery, both the diodes do not conduct. Now the output voltage is plus 5 volts because there is no current flowing through RL. Okay, so this is how AND gate is working, and its Boolean expression can be represented as A and B is equal to Y. This is here the AND operation is represented by a dot, and this is called AND. So A and B is equal to Y is the Boolean expression, and this Boolean expression operation is like this: 0 and 0 will give you 0, 0 and 1 will give you 0, 1 and 0 will give you 0, 1 and 1 will give 1. This is like the usual multiplication. Okay, so this is about AND gate, and next one is NOT gate. It is also known as inverter because whatever be the input, the output will be the reverse or the inverted quantity of this input. So this is NOT gate, and this is the simplest of all logic gates. It has only one input and one output. Okay, and the Boolean expression truth table is like this: if the input is 0, output is 1, input is 1, output is 0. That's why it is known as inverter. Okay, the circuit diagram is like this, and here we are using transistor. Okay, so the transistor inverts the input. When A is connected to the ground, this is A connected to the ground, the base transistor, the base of the transistor Q1 will become negative. This negative potential causes the transistor to cut off, and the collector current is 0 and the output is plus V volt. So plus V volt is given at the end of RL. So the negative potential causes the transistor to cut off and collector current 0 and output is plus V volt. In binary terms, when A is equal to 0, Y is equal to 1. So that's the point. Similarly, if sufficiently large positive voltage is applied at A, the base of the transistor will become positive, causing the transistor to conduct heavily. Therefore, the output voltage is 0. In binary form, we can represent A is equal to 1, Y is equal to 0. So this is the truth table, and this is the symbol. Okay, and the Boolean expression for NOT gate can be represented as Y is equal to A bar. Y is the output, A is the input. So the output will be the inverted value of the input. A is equal to 0, Y is equal to 1. A is equal to 1, Y is equal to 1, 0. So this is the these are the three basic logic gates. Now we can see the combination of basic logic gates. The first one is NAND gates, or AND NOT gates are the three basic circuits that make up all digital circuits. Now we shall discuss some combination of this. First one is NAND gate. NAND gate is a combination of AND gate and NOT gate. So it is clear from this name itself. NOT gate and AND gate will give you NAND gate. In other words, output of AND gate is connected to the input of NOT gate. Clearly, the output of an AND gate is possibly an AND gate is opposite to the AND gate. So what is doing here? The output of AND gate is connected to the input of NOT gate. Clearly, the output of NAND gate is opposite to the AND gate because it is getting inverted by the NOT gate. This is illustrated in the truth table of the NAND gate. Note that truth table for NAND gate is developed by inverting the outputs of AND gate. The Boolean expression for NAND function is y is equal to a and b inverted. So the output value of AND gate is getting inverted by the inverter amplifier. So that will give you the NAND gate output. This Boolean expression can be read as y is equal to not a and b. To perform the Boolean algebra operation, sorry. To perform the Boolean algebra operation, first the inputs must be ANDed and then the inversion is performed. So we are giving the inputs at the AND gates. This is the AND gates, and we are getting an output, and this output is getting is feeding into the input of a NOT gate. So the result will be like this. Note that output from NAND gate is always 1 except when all of the inputs are 1. So it is clear from this truth table. A is equal to 0, 0 means after AND operation the output will be 0, and this is 0, this is 0, this is 1, and if it is getting inverted the result will be 1, 1, 1, 0. Okay, so the final output for this input values are this 1, 1, 1, 0. So the symbol of this NAND gate is this AND gate combined with a NOT symbol. So this is the symbol of NAND gate. And the another combination gate is NOR gate. It's a combination of OR gate and a NOT gate, in which what we are giving is the inputs are given to the OR gate and its output is feeding to the input of NOT gate. So the result will be the inverted value of the OR gate. Okay, if A and B are the input, the output of the first gate is A plus B, and it is getting inverted after this inverter. So A plus B whole bar. Okay, so this is the truth table representing this. The Boolean expression for NOR function is y is equal to A plus B whole bar, where NAND gate is A and B bar. Okay, this expression can be read as y is equal to not A or B. To perform the Boolean algebra operation, first the inputs must be ORed and then the inversion is performed. Note that the output from a NOR gate is high only when all the inputs are low. If any of the input is high, the output is low. This is clear from this truth table. And this is the logic symbol of NOR gate. OR gate with the NOTed value. So this is the symbol of NOR gate. Okay. Now so NAND gate is a universal gate because its repeated use can produce other logic gates. The table below shows how NAND gates can be connected to produce inverter, that is NOT gate, AND gate and OR gate. So NAND gate is known as a universal gate because the combination of this can be used to produce other logic gates. Okay, this table give the combination of this AND gates which produce AND, OR and NOT gate. So the NOT gate can be constructed using the AND gate by this. NAND gate by this. Here both the inputs are same and the output will be the complement of this. So this is equivalent to a NOT gate or inverter. And here inputs are given the NAND gate. So this will be Y bar, that is a NB bar, and this is given as input to both the terminal of NAND gates, and the output will be Y. Okay, so the output is similar to A and B. And similarly OR gate. So if we are summing the result of these two, we are getting A or B at the output. So this is how we are constructing AND, OR and NOT gate using NAND gate. Okay. Sorry, this page is not changing. I am trying to change. Now the next one is exclusive OR gate. Exclusive OR gate. The name exclusive OR gate is usually shortened to Xor Gate. The Xor Gate can be obtained by using OR, and NOT gates. So exclusive OR gate is also known as XOR Gate. Xor Gate that can be obtained by using OR and NOT gates. Okay, this figure shows the truth table of Xor Gate. Okay, the table shows the output is high if any but not all the inputs are high. So the output is high only if any of the input is high, not when all the inputs are high. If all the inputs are high, the output is 0. Okay, so this is the truth table for Xor Gate. The OR gate truth table is also given so that you can compare the OR gate with the truth table of that of Xor Gate. The logic symbol for Xor Gate is shown here, that is an OR gate with an additional curved line here. So this is the Xor Gate. Now the symbol is similar to OR gate except an additional curved line at the input side. Okay, so this is Xor Gate. Not changing. So its operation is given here in an expanded form. Here the inputs are A, B. So we are giving 0, 0 to A and B, and the inverted value will be 1 and 1. So A bar B is equal to Y bar, A dot B bar is equal to Y W bar. So Y is equal to Y bar plus Y double bar, which is 0. So we can check each value like that. So this is about exclusive OR gate. Now let us see what is De Morgan's theorem. So let's quickly go to that page. De Morgan's theorem. Yeah, here it is. De Morgan's theorem. I'm quite De Morgan's theorems are extremely useful in simplifying expressions in which a product or sum of variables is inverted. The two theorems are first one is A plus B whole bar is equal to A bar and B bar. Similarly, second theorem is A and B whole bar is equal to A bar plus B bar. The first De Morgan's theorem may be stated as under: when the OR sum of two variables is inverted, this is equal to inverting each variable individually and then ANDing these inverted variables. So this is the first theorem. Hope you have got the idea. So this theorem is extremely useful in simplifying expressions in which product or sum of variables is inverted. So such expressions can be simplified using this theorem. Okay. So this first theorem states that when the or sum means A or B, or sum of two variables here is A and B, is inverted. Inverted means A plus B whole bar. This will be equal to inverting each variable individually, that is A bar, B bar, and then ANDing these inverted variables, that is A bar and B bar. So this is the first theorem. In this expression, A and B are two variables. The LHS is the complement of the OR sum of the two variables. The RHS is the AND product of individual inverted variables. Now the second De Morgan's theorem may be stated as under: when the AND product of two variables is inverted, this is equal to inverting each variable individually and then ORing them. Then that will give you A and B whole bar is equal to A bar plus B bar. In this expression, A and B are the two variables. The LHS is the complement of the AND product of the two variables. The RHS is the OR sum of the individual inverted variables. So this is the De Morgan's theorem. These are the De Morgan's theorem. So we have discussed all the universal logic gates and De Morgan's theorem, etc. So we conclude this module here with these topics. Okay. Thank you.